In this lesson, we're going to learn about the discriminant and the nature of roots for a quadratic equation. The expression b squared minus 4ac is the discriminant. It's a part of the quadratic formula. Three different situations can occur because the discriminant is inside of a radical. The discriminant can either be positive, 0, or negative. That covers every situation. If it's positive, the result of the quadratic formula will be to give two unequal real roots. If the discriminant is 0, we get two roots that are equal to each other. If the discriminant is less than 0, we get no real roots at all. Here are three example quadratic functions or equations that I'm going to use the quadratic formula on. In the first case, x equals 2 plus or minus negative 2 squared minus 4 times a times c, which is 0, and over 2a. This simplifies to 2 plus or minus, that's 4 in a radical, so 2 plus or minus 2 over 2, and therefore x is either equal to 4 over 2, which is 2, or 2 minus 2, which is 0, and we see that we get two different roots. Now, if the discriminant is 0, let's look what happens here. In this case, x equals 2 plus or minus negative 2 squared minus 4, a is 1, and c is 1. So the only thing that differed in this case was c, over 2 times 1. So x equals 2 plus or minus 4 minus 4. In a radical, 0 in a radical is 0. 2 plus 0 and 2 minus 0 are the same thing. I end up with x equals 1 twice. I get the same result twice, so I get two roots that are equal to each other. The third scenario, all I did was differ c, and when I put this into the quadratic formula for c is now 2, notice that, by the way, notice that the only thing that's changing on each of these is the discriminant, which is the point of this lesson. 4 minus 8. I get the root of negative 4. Well, the root of negative 4 is non-real. I don't get any answers at all. These are examples to show the three different things that can happen. This is referred to as the nature of the roots. So if you're asked in a question, what are the nature of the roots, the goal is to use the discriminant and determine which case you have, and therefore, do you have two different roots, two of the same root, or no roots at all? Let's look at an example of that in a moment. One other thing I would like to do, though, is I'd like to highlight graphically, in terms of functions, what those three examples look like. A, B, and C correspond to the information above, and you'll notice that the first function could be factored, as presented here. The second one can also be factored, as presented here, and I'd just like to highlight that the first function has two zeros at 0 and 2, as we found out. The second function has a 0 at 1 only, and the third function, which is up higher, has no factors at all and doesn't touch the axis at all. Now, just in case you misunderstand, it's not specifically whether or not something factors to tell whether or not you will get zeros or roots, but it does illustrate very simply in this case, because it factors, that we can easily find the x-intercepts or zeros, and those do correspond to the roots, and that the first case has two crossings on the x-axis, the second only one, and the third none at all. Now, about the nature of roots. Here are three example questions. The nature of the roots refers to analyzing b squared minus 4ac to determine if it's greater than, equal, or less than 0. So in this case, b squared minus 4ac is 16 minus 12, or 4. 4 is greater than 0, so therefore I have two unequal real roots. It's as simple as that. Second one, you may want to pause, try it, and then check your work against mine. There's your A, there's your C. I have 16 minus 16. It is 0, and therefore I have two equal real roots. Third case, 4 squared minus 4ac. 16 minus 20 is negative 4, which is less than 0, and therefore I have no real roots. So that's how nature of the roots works. Again, we're not solving to find the answers or the roots. We're just trying to determine what scenario exists. Now, a couple of trickier questions you might be asked. Find an unknown value, like k, in a situation. So here's a quadratic equation. There's a coefficient k that's not given to us, and we're asked to find one real solution. Well, one real solution means that b squared minus 4ac needs to equal 0. So my b is the coefficient on x, that's k, b squared minus 4ac. I need it equal to 0 because I want one real solution. So k squared minus 40 equals 0, so k squared equals 40, and k therefore equals positive or negative root 40, or taking the perfect square out, 2 root 10. There are actually two values of k that will give you one real solution. This next one's even slightly trickier. I want no real solutions in this scenario, and notice that k is in two locations. No real solutions means that b squared minus 4ac will be less than 0. Let's have a look at that. B squared. Well, that's b squared minus 4. A is k, c is k, the coefficient on x squared and the constant. And I need it less than 0. So 25 minus 4k squared is less than 0. Now, I can write 25 less than 4k squared, 25 over 4 less than k squared. Now at this point we have to be careful. The answer is not k greater than plus or minus 5 over 2. If we think about a number line of k values, think about 5 over 2 and negative 5 over 2. So negative 2.5 and positive 2.5. So values in between could be 0, 3 is greater than, and negative 3 is less than. Think of values whose square is more than 25 over 4. Well, if I say 0, 0 squared is not more than that. So this is not the region that I want. If I substituted 3 here, 3 squared are 9. Well, 25 over 4, that's 6 and a little bit. 9 is more than 6 and a little bit. So that works. As will negative 3, because negative 3 squared is also 9. So the regions that I want are actually over here to the left, going off to the left forever, and over here to the right, going off to the right forever. So if I thought that the answers were this, plus or minus 5 halves, and more than that, what that's actually saying is these values to the right, well, that's good so far. But here's where I have a problem. Greater than negative 5 halves. These values are not right. This is wrong. So we don't want to say that. What we do need to do is one of two things. And this all has to do with inequalities of quadratics. That's what makes this one tricky. You can either say the absolute value of k itself, see this takes care of the sign issue, is more than 5 over 2. This corresponds with this graphic up above. The other way that I can say it is k is less than negative 5 halves, or k is greater than positive 5 halves. This says the same thing as this, and both are supported graphically, visually, by that number line up above. Now, one other option that's available, if you want to organize your thinking a little bit, we could write something like this. An interval of values, a test value, and the actual value in the expression, so k squared, and then is it greater than 25 over 4? So in an interval where k is less than 5 halves, a test value could be negative 3. Negative 3 squared is 9. Is 9 more than 25 over 4? Yes, it is. So this is the right interval. in an interval like, I don't want 0 specifically, 0 is a test value, a value more than 5/2 but less than positive 5/2. Test value of 0, 0 squared is 0. Is that more than this? No, it is not. That's the wrong interval. And third, try a value more than 5/2, like 3, for example. 3 squared again is 9. 9 is more than this, and so I found my intervals. These are the k values that satisfy the equation.